If the numbers coming out of Pozzuoli right now have your attention, take a second and subscribe to Orbital View. We're tracking this system closely: the INGV bulletins, the new research, the geochemical signals. Drop a comment below. If you live in the Naples area or you have family there, has anything changed in how you think about it? I read every one. Here's what we're getting into today. A magnitude 4.4 earthquake that struck 2 days ago, directly over a fault line that scientists didn't know was there until a Stanford AI revealed it last year. The research showing the crust beneath the caldera is now about one-third as strong as it was the last time they had to evacuate. And a paper published just weeks ago that put a specific date range on where the current acceleration ends, a critical transition, projected for the early 2030s, that the researchers describe as a point the accumulated stress must be released. Let's get into it.
2 days ago, at 3:50 in the morning local time, the ground west of Naples moved. The Italian National Institute of Geophysics and Volcanology, INGV, logged it at magnitude 4.4. Depth approximately 3 kilometers. The epicenter placed it between the municipalities of Pozzuoli and Boccoli, in the Gulf of Pozzuoli, directly in the offshore sector of the caldera. A swarm of 12 additional events followed before midday. By that afternoon, officials in Naples had ordered precautionary school closures in the Bagnoli and Fuorigrada districts, the western neighborhoods of Naples that fall inside the red zone, while inspectors checked public and private buildings for structural damage. This is the event. This is what the headline is about. And if you read the coverage, what you mostly got was powerful earthquake swarm near Naples' Supervolcano. The kind of framing that lands and fades within a news cycle because it happens often enough now that it no longer fully surprises people. But here's what that framing leaves out. The magnitude 4.4 is not the part of this that matters most. The location is. And to understand why the location matters, you need to know about a piece of research published last September in the journal Science. Research that quietly changed what scientists understand about the architecture of the system the earthquake just hit. For years, the seismicity at Campi Flegrei was frustrating to map with precision. The earthquakes were there, thousands of them, building over more than a decade, but their spatial structure was blurry. The picture was too incomplete to resolve. Then a team from Stanford University, working with INGV at the Vesuvian Observatory in Naples, applied a retrained machine learning workflow to the raw continuous seismic data from January 2022 through March 2025. What they found rewrote the map. The catalog expanded from approximately 12,000 earthquakes to more than 54,000. 4 times as many events had been hiding in the data. And when they plotted those 54,000 events, the picture that emerged was stark. A sharply defined ring fault system tracing the edge of the caldera, concentrated in an extremely narrow depth range. A thin, clear line. The Stanford geophysicist Gregory Barroza described it plainly. Previously, the structure of seismicity in the caldera was indistinct. Now they had seen a very thin and well-marked ring fault consistent with the surface features, and consistent with the area being uplifted. The swarm that struck 2 days ago was concentrated directly along that ring fault. The earthquakes in the current swarm had hypocenters between roughly 1 and 3 kilometers deep. That shallowness is not unusual for Campi Flegrei. It is actually the signature of bradyseismic seismicity, driven by the rising of the ground rather than by the activation of deep fault plains. But the position matters. The AI imaging revealed for the first time that the ring fault is not an abstract construct. It is a physical structure, and it is being progressively activated by the same pressure that has been lifting the ground for 21 years. So, 12 events, magnitude 4.4 at the top, school closures in Naples, and a ring fault that only became visible to science 9 months ago, now registering that same fault being stressed in real time. That is what happened 2 days ago. And the reason the researchers who study this system are alarmed is not because this swarm was unprecedented. It's because of what it represents in context. The context is the part the news coverage didn't have room for. This is the part I want to walk you through. The ground beneath Campi Flegrei has been rising continuously since 2005. As of early 2026, INGV's instruments are recording ground uplift at 10 millimeters per month. That rate has held for over a year. The cumulative total since 2005 is approximately 140 centimeters, roughly 4.5 feet of sustained ground lift over 2 decades. The largest earthquake recorded in the current cycle hit magnitude 4.6 on June 30th, 2025. 5 separate earthquakes above magnitude 4 have occurred during 2025 alone. None of that is normal caldera behavior. And the reason it isn't normal becomes clear when you understand what bradyseism is. not as a word, but as a physical process, and why the version currently underway is different in kind, not just degree, from the episodes that came before it. That's where we go next. The most important piece of geological evidence in this entire investigation is not a seismograph readout or a gas emission measurement. It's 3 marble columns standing in the town of Pozzuoli, about a kilometer from the coast. They're Roman. They were part of a macellum, a market building, constructed sometime around the 1st or 2nd century of the Common Era. They've been standing there for roughly 2,000 years, and in that time, the ground beneath them has moved so dramatically that the columns became, without anyone intending it, the world's most precise long-term ground movement record. Halfway up each column, there's a band of burrow holes, the work of lithodomous mollusks, marine bivalves, that drill into rock only when it's submerged in seawater. The borings are unmistakable. They mean the columns were underwater, not for a day or a week, for long enough for a colony of marine animals to establish themselves and hollow out the stone. According to the Global Volcanism Program at the Smithsonian, the ground at Pozzuoli sank 11 meters below sea level by around 1000 of the Common Era, then rose 12 meters by 1538, including a rapid uplift of 4 meters in the years immediately before that year's eruption. The ground has been breathing at Campi Flegrei for at least 2,000 years. The columns have been recording every breath. Bradyseism, from the Greek for slow movement, is the technical name for this. It's the gradual uplift or subsidence of the caldera floor, driven by pressure changes in the magmatic and hydrothermal systems below. The ground doesn't just shake at Campi Flegrei. It rises and falls on timescales of years to decades, carrying with it every building, road, harbor, and human life sitting on top of it. When it rises, the harbor fills in. The seafloor comes up to meet you. Streets crack and buckle. When it falls, the sea rushes back in. The columns disappear below the waterline. The marine mollusks get to work. The caldera has been doing this in cycles. In the modern era, since systematic measurement began, there have been 4 distinct episodes of unrest: 1950 to 1952, 1969 to 1972, 1982 to 1984. And then, beginning around 2004 or 2005, the current episode, which is still ongoing. Each of those first 3 episodes produced significant uplift and then stopped. The ground came back down, life resumed. The 1982 to 84 episode was the most severe in modern recorded history. More on that in detail later, and even that one eventually subsided. The evidence from those cycles fed a reasonable hope that this is what Campi Flegrei does. It breathes hard for a while, then settles. It has done this before. It will do it again. But a paper published just 4 weeks ago, April 28, 2026, posted to the preprint server archive by a team led by Davide Zaccagnino, is not compatible with that framing. And the reason it isn't compatible isn't a matter of opinion or interpretation, it's mathematics. Here's the distinction that matters. In a normal accelerating process, an exponential one, the rate of increase grows at a fixed percentage. It's fast, it gets faster, but the rate of acceleration itself is constant. You can model it, extrapolate it, plan for it. The current unrest at Campi Flegrei doesn't fit that model. Zaccagnino and his colleagues found that the combined acceleration of seismicity and ground deformation fits a different pattern, what physicists call a finite time singularity. This is not exponential. In a finite time singularity, the rate of acceleration is itself accelerating. The foot is going deeper and deeper on the pedal, and the pedal itself is getting easier to push. The equations that describe the system stop working in their current form at a specific point, a singularity, a critical transition, and the system is forced into a new regime. That transition has a projected time frame. Independent analyses using multiple methods converge on a critical point. Zaccagnino's team writes it as T sub c of approximately 2030 to 2034. By that time, cumulative uplift is projected to reach approximately 4 meters. 4 meters. Since 1950, the total uplift at Pozzuoli across all 4 modern episodes has been approximately 4 meters. The system is approaching the same total again, but not across 4 separate crises, in one sustained accelerating push. I want to be very careful about how I hold this, and about how I ask you to hold it too. The Zaccagnino paper explicitly states that no evidence of imminent eruption was found. The outcome of the critical transition is uncertain. It could be eruption. It could be a bradyseismic peak followed by subsidence. It could be another regime change entirely. The paper doesn't tell us which. What it tells us is that the system is approaching a threshold, and that the nature of the acceleration is categorically different from previous episodes. That distinction matters, because previous episodes could reasonably be described as the caldera breathing. This one is starting to look like the caldera holding its breath. Let me tell you about a ceramic mug. If you heat a ceramic mug with a hairline crack, cool it down, heat it again, cool it again, the crack doesn't stay the same. It extends. Millimeter by millimeter, the fracture propagates through the material. Each thermal cycle does permanent damage. You cannot uncrack what's already cracked. You can run that cycle enough times that eventually, under a stress that the mug would previously have handled without trouble, it simply breaks. This is what 70 years of Braticism has done to the crust of Campi Flegrei. In 2023, a team from University College London and INGV, led by the volcanologist Christopher Kilburn at UCL, published a study in Nature's Communications, Earth and Environment that calculated what decades of uplift and subsidence have done to the tensile strength of the rock above the caldera's pressure source. Tensile strength is the maximum stress a material can bear before it breaks under tension, before it's pulled apart. The team modeled the caldera's crust as it has been progressively deformed across each unrest episode since 1984. Their finding, the current tensile strength of the crust is likely about 1/3 of what it was in 1984, 2.5 to 3 times smaller. The rock is not just under more stress than it was 40 years ago, it is fundamentally weaker. The material itself has been altered by repeated stretching, fracturing, and partial healing. Every episode leaves the next one starting from a point of greater vulnerability. As Kilburn put it, at each emergency, the crust is being stretched just that bit further, so the later emergencies are building on the previous ones. The team had actually predicted this in advance. Back in 2016, they modeled the system and concluded that continued approach to rupture would be confirmed by an additional uplift of 30 to 40 centimeters at the point of maximum movement. That additional uplift has since occurred and been exceeded. The 2023 paper was, among other things, a confirmation of a 7-year-old prediction. Now put that finding alongside something else. The Stanford team's AI expanded seismic catalog revealed for the first time not just the ring fault, but also the strict depth ceiling of the seismicity on that fault. To date, per the science paper, no seismic activity below 3.7 kilometers has been observed on or inside the ring fault system. 3.7 kilometers, that's an important number. It means the earthquakes illuminating the ring fault are all shallow, happening in the brittle, fractured zone that the hydrothermal system is pressurizing from below. It also means we're not yet seeing direct seismic evidence of magma pushing up through deeper rock. The pathway isn't lit from below yet, just from above. And then there's the January 2025 paper. This one appeared in Nature Geoscience. A different journal, a different team, a different measurement. Led by Stefano Caliro and colleagues at INGV's Vesuvian Observatory in collaboration with the University of Palermo, the University of Cambridge, and the Woods Hole Oceanographic Institution. What they measured was not ground movement or earthquake frequency. They measured the sulfur. Since the end of 2018, the fumarole emissions at the Solfatara crater in the heart of the caldera have been releasing an increasing proportion of what the researchers call isotopically light sulfur. This is a chemical fingerprint. Normal hydrothermal sulfur carries a specific isotopic signature, a ratio of sulfur 32 to sulfur 34 that reflects the temperatures and chemical conditions of a hydrothermal reservoir. The signal since 2018 is different. The sulfur being released is isotopically lighter. And the only mechanism that produces that signature, according to Caliro's team, is decompression-driven degassing of mafic magma, fresh, deep magma releasing gases as pressure on it decreases, at a depth of 6 kilometers or more. 6 kilometers. Below the 3.7 kilometer depth ceiling of the ring fault seismicity, below the hydrothermal system. This is a signal from something deeper. Caliro's paper describes the changes as unprecedented in the multi-decadal observational record. Similar sulfur signals were seen during the 1982 to 84 crisis, but the current changes are more pronounced, suggesting, in the words of the commentary accompanying the paper in Nature Geoscience, different underlying processes. The summary published by the Vesuvian Observatory's press office says plainly, the team has identified an important anomaly in the composition of the gases of the fumaroles, linked to the contribution of magmatic gases. So, a ring fault now sharply illuminated being activated by this week's swarm. Crust 1/3 its 1984 tensile strength. A finite time singularity model projecting a critical threshold by 2030 to 2034. And a geochemical signal since 2018 indicating degassing magma at 6 or more kilometers depth, a signal that has no hydrothermal explanation. Each of these measurements came from a different instrument. Each came from a different team. Each was published in a different journal. None of them was designed to confirm the others. And they all tell the same story. That convergence is the part that has the researchers paying close attention. Before I go further, I want to spend some time in the chemistry. because it's one of the most underreported threads in this entire investigation, and it carries information that the seismic and geodetic data alone can't provide. Think of the caldera's gas emissions as a language. Different gases carry different messages, and the ratio between them, the temperature at which they emerge, the isotopic signature they carry, all of it is a readout of what's happening at depth. Volcanologists have been reading that language at Campi Flegrei for decades. And what the language has been saying since around 2018 has shifted in ways that are, in the technical literature, described as unprecedented. The primary venting sites are two. Solfatara crater, roughly in the center of the caldera, a broad, flat-floored maar whose entire surface steams and hisses and reeks of hydrogen sulfide, one of the most active surface degassing structures in Europe. And approximately 400 meters to the east, the Pisciarelli fumarole field, a smaller, more intense site where the main vent, called the Soffione, emits at extraordinarily high rates. The CO2 numbers are the place to start. Carbon dioxide is the early signal from depth. Because of its low solubility in magma, CO2 comes out of solution deep in the system. It travels upward through the rock before any other volcanic gas, arriving at the surface well ahead of what might follow. By the time CO2 flux starts climbing, the system below has already been pressurized for some time. At Pisciarelli's main vent, CO2 flux increased by a factor of more than 3 between 2012 and 2018 to 2019, reaching levels exceeding 600 tons per day. 600 tons per day from a single fumarolic vent field less than a quarter of a square kilometer in size. That figure, as published by Giancarlo Tamburello and colleagues at INGV in 2019, is comparable to the emissions of a medium-sized erupting arc volcano. The ambient air near Pisciarelli has measured carbon dioxide concentrations up to 6,000 parts per million. Atmospheric background is roughly 420. These are not rounding errors. But CO2 is the early courier. It tells you pressure is building from depth. What comes after? What tells you the magma itself is getting closer to the surface is sulfur dioxide. SO2 appears when magma is degassing at shallow depth. And for most of the current unrest episode, the dominant sulfur species at Campi Flegrei has been hydrogen sulfide, H2S, which forms when SO2 is converted at hydrothermal temperatures and pressures before it reaches the surface. That conversion is consistent with a deep source, with the gas being scrubbed through the hydrothermal system on its way up. This is the critical context for the Calero 2025 Nature Geoscience paper. What that paper identified is not just elevated sulfur, it's a change in the isotopic character of the sulfur being emitted. Since 2018, the fumaroles have been releasing increasing amounts of isotopically light sulfur-32 relative to sulfur-34. That specific isotopic shift is the signature of decompression-driven degassing of mafic magma at depth. The hydrothermal system alone cannot produce this signal. Something deeper is contributing. The commentary accompanying the Calero paper in Nature Geoscience, written by volcanologists at the French CNRS and the University of Florence, described the finding this way. While similar signals were observed during the 1982 to 84 crisis, the current changes are more pronounced, suggesting different underlying processes. More pronounced than the crisis that forced the evacuation of 40,000 people. And the ING Vesuvian Observatory, in its own press release, used language that doesn't appear in its weekly seismic bulletins. The team identified an important anomaly in the composition of the gases, linked to the contribution of magmatic gases. Now hold all of that together. CO2 at 600 tons per day from a single vent, erupting volcano scale. Isotopically light sulfur appearing since 2018 from a source 6 or more kilometers deep. Temperature at the Pisciarelli main fumarole holding at around 94 degrees Celsius. 4 geochemical monitoring stations running continuously in the Solfatara and Pisciarelli areas, and a multi-decadal record that has been moving in one direction for over 2 decades. The language the caldera is speaking has not been ambiguous. It has been escalating methodically in every channel simultaneously, seismic, geodetic, geochemical, with each channel carrying the same underlying message about what is building from below. The question the evidence forces is not whether something is changing. That's settled. The question is what it is changing toward. There's a particular kind of scientific result that lands differently than most. Most findings add a data point, refine an estimate, advance a conversation. Some reframe the entire question. The April 2026 preprint from Davide Zaccagnino and colleagues is the second kind. What Zaccagnino's team did was mathematically characterize the type of acceleration happening at Campi Flegrei. Not just how fast it's accelerating, but the shape of the acceleration itself. And the shape matters enormously, because different shapes imply different physics, different endpoints, different levels of urgency. The distinction between exponential growth and a finite time singularity is not technical jargon. It is the difference between a system that is accelerating and a system that is converging. Exponential growth, fast, getting faster at a fixed rate, can in principle continue indefinitely. It is startling. It is concerning. But it doesn't have an intrinsic endpoint built into its mathematics. A finite time singularity is different. The acceleration is itself accelerating, and it does so in a way that the equations physically cannot sustain beyond a certain point. The system is not just moving towards something. It is converging on a critical transition, a point at which the current dynamic regime must change. Think of it this way. Water in a pot heats exponentially, but when it crosses 100 degrees Celsius, the regime changes. It boils. The finite time singularity is the mathematical description of a system approaching its boiling point. What comes after is not necessarily catastrophic, but the current regime cannot persist. Zaccagnino and his team applied this framework to the combined acceleration of seismicity and ground deformation at Campi Flegrei since the current unrest began. Independent analyses using multiple methods converged. The critical transition point, written in the paper as T sub c, lands at approximately 2030 to 2034. By that point, cumulative uplift is projected at around 4 meters. And the paper uses language that is carefully chosen. The system appears to be approaching a critical mechanical threshold whose outcome remains uncertain, requiring sustained high-resolution monitoring and continuously updated forecasts. I want to read that carefully with you. Critical mechanical threshold, meaning the rock itself is the limiting factor. Outcome remains uncertain, meaning the paper does not predict eruption. It predicts that the current state cannot continue past a certain point. What replaces it is what we don't yet know. Requiring sustained high-resolution monitoring, meaning this is not a warning to panic, it is a call for attention. The commentary published in Indian Defense Review, reporting on the Zaccagnino paper in May 2026, quoted a description of the distinction between exponential and finite time singularity. This distinction is crucial for predicting whether the volcano's crust will fail and what form that failure might take. The team is developing a continuous forecasting system that updates predictions as new seismic and geodetic data arrive. Also published in March 2026, Sebastian Heinzel and colleagues in Communications, Earth, and Environment, a new deformation-driven earthquake interaction model confirming that the Campi Flegrei seismicity is closely linked to ground uplift through a cascading, nonlinear process. The complexity of the earthquake patterns is not random noise. It is structured. It follows from the deformation, which follows from the pressurization, which follows from the magmatic volatile input that Caliro's team identified at depth. 5 independent research outputs, 5 different methods, 5 different journals or preprint servers, the Kilburn Tensile Strength Study, the Stanford AI Ring Fault paper, the Caliro Sulfur Isotope paper, the Heinzel Deformation Earthquake Model, and the Zaccagnino Singularity Projection. None of them was designed to confirm the others, and they all point to the same place. The caldera is not just restless, it is approaching something. The science now has a projected window for when that something arrives, and 500,000 people live inside the ring.
That is where Chunk 1 ends. In Chunk 2, we go deep, inside the mechanism that drives this whole system, the historical cases that show what it has done before, and the specific compound threat that most of the coverage isn't discussing.
Before we go into the history, I want to take you inside the engine, because the thing driving all of it, the swarms, the uplift, the gas, the cracking crust, is not a single process. It's a layered system, and each layer feeds the one above it. Understanding that architecture is what makes the historical cases land properly. And it's what makes the current measurements alarming in a way that the previous episodes weren't. Start at the bottom. At approximately 4 kilometers below Pozzuoli, this is based on petrological and seismic data from multiple studies, sits a magma source, not a pool of liquid rock ready to pour. Volcanologists describe it as a magmatic sill, a lens-shaped body of partially molten material, probably trachytic in composition, that has been sitting there for an extended time. But below it, and this is where the Caliro 2025 Nature Geoscience paper becomes critical, there is also evidence of something deeper. Decompression-driven degassing of mafic magma, fresh, hotter, less evolved magma, at 6 or more kilometers depth. This deeper source appears to be the driver of the isotopically light sulfur anomaly. It is releasing volatiles, primarily CO2 and sulfur gases, that rise through the system, interact with the hydrothermal reservoir, and ultimately emerge at the surface through the Solfatara and Pisciarelli vents. The hydrothermal system is the middle layer. Think of it as a vast pressurized reservoir of superheated water and gas, sitting between the magmatic source below and the surface above. It's not water in any recognizable sense. At depth, at those temperatures and pressures, It's a supercritical fluid, neither fully liquid nor fully gas, with properties that change dramatically with small shifts in temperature or pressure. When the magmatic input below increases, when more gas is delivered from depth, the hydrothermal reservoir pressurizes. That pressurization does two things simultaneously. First, it pushes the ground up. The fluid pressure in the rock pores is increasing, the rock expands, the surface rises. Brady sees them. Second, it fractures brittle rock. When the pore pressure in the rock exceeds the confining stress. When the fluid is pushing outward harder than the rock can hold, the rock breaks. Earthquakes. Shallow earthquakes in the brittle zone above the hydrothermal reservoir between roughly 1 and 4 kilometers depth. This is the mechanism. Magmatic volatile input from below pressurizes a hydrothermal reservoir, which inflates the ground and shatters rock. Both the uplift and the seismicity are symptoms of the same underlying cause. But there's a feedback built into this system that makes it self-reinforcing. The Stanford science paper identified, within the expanded seismic catalog, a population of very shallow hybrid earthquakes, events with unusual waveform characteristics that suggest they occur at the boundary between the hydrothermal reservoir and the cold rock above it. These events are, per the paper, likely related to the hydrothermal system's dynamics. What causes hybrid earthquakes at that boundary is typically the rapid flashing of superheated liquid water into steam, a phreatic process driven by the earthquakes themselves. The shaking fractures rock. Fractures allow cold groundwater to reach hot hydrothermal fluid. The resulting steam flash generates another pulse of pressure, which fractures more rock, which allows more water in. The system can be self-exciting. A July 2025 paper in Communications, Earth and Environment analyzing earthquake source mechanisms and waveform similarity at Campi Flegrei identified newly observed very long period signals, VLP events, whose source is located at approximately 3.6 kilometers depth between the proposed inflation source and the Solfatara Mare. VLP events are associated with large-scale fluid movement, resonance in a fluid-filled crack or conduit. Finding them now at this depth in this location means the plumbing connecting the deep source to the surface is not just a diffuse seep. It has structure. There are conduits. And those conduits are oscillating. So the architecture of the machine is this: a deep mafic source at 6 or more kilometers releasing volatiles. A sill-like magmatic body at around 4 kilometers amplifying the pressure signal. A hydrothermal reservoir pressurizing the brittle crust above it, self-reinforcing fracturing as water meets heat. A ring fault progressively illuminated by the accumulation of all of this. And at the surface, the Solfatara steaming, Pisciarelli venting at 600 tons of CO2s per day, the ground rising 10 millimeters every month, and the Pozzuoli harbor being periodically dredged because the seafloor keeps climbing. Every measurement coming from this system is a readout of the same machine running harder, and the machine has run before, not at this intensity. But it has run. And what it did when it ran before is the evidence that makes the current readings comprehensible. Most people who know Campi Flegrei know it as Europe's supervolcano. Dangerous. Potentially catastrophic. Last erupted in 1538. That last eruption is typically mentioned as a brief historical footnote, a reassuring one even, almost 500 years ago. The implication being, whatever it does infrequently. The truth is more complicated. And the specific sequence of events that led to 1538 is one of the most directly relevant pieces of evidence for what is happening now. Start with the columns. The marine borings that reach mid-column on the Serapeum pillars tell us the ground at Pozzuoli had been sinking for roughly 1,000 years before 1538. Sinking slowly, steadily as the caldera deflated, then somewhere around the early 1400s, the historical record becomes usable around 1430. The ground started rising again. A study published in 2024 reconstructed the chronology in detail. The uplift affecting the whole caldera began increasing from around 1400 to 1536, with the maximum consistently in the Pozzuoli area. Then, from 1536 to 1538, the character of the uplift changed. It focused. Instead of caldera-wide deformation, it concentrated in the area that would become the eruption site. The rate accelerated sharply. The eyewitness accounts from the days immediately before the eruption are vivid. According to De Vito and colleagues, all historical sources coeval with the eruption report evident uplift accompanied by seismicity and opening of fractures in the vent area during the 2 days that preceded the eruption. On the 28th of September, 1538, about 20 tremors were felt between daybreak and nightfall. The sea pulled back from the shore, the ground cracked open. And then, on the 29th of September, the eruption began. In 1 week, Campi Flegrei built a mountain. Monte Nuovo, New Mountain, rose approximately 123 meters above the landscape in 7 days. It was a hydromagmatic eruption, magma meeting groundwater and seawater, generating enormous explosive energy. The eruption opened with explosive phases, built a cone around the vent, and ended on October 6th with a violent explosion that killed 24 people who had climbed the cone to observe the activity, believing it had quieted. The cone they were standing on then partially collapsed. The eruption was over, but the mountain remained. Monte Nuovo still exists. It's a forested hill on the coast near Pozzuoli, about 2 kilometers from the town center. You can hike it. It takes about 30 minutes. It is a hill that did not exist on September 28, 1538. That is the kind of thing this caldera can produce. Now here's the comparison that the Natural Hazards and Earth System Sciences paper, published in September 2025, makes explicit. The maximum magnitude of the current unrest, 4.6 recorded in March 2025, is very similar to the maximum magnitude reconstructed for the period 1430 to 1503, the early phase of the pre-eruption unrest. The average uplift rate since 1950 is comparable to the average uplift rate in the first 70 to 73 years of the pre-1538 sequence. And the pre-1538 sequence ran for roughly 100 years before culminating in the eruption. That comparison is not presented as a prediction. The paper explicitly notes it is constructing scenarios for civil protection purposes, not issuing a forecast. But the structural similarity is the reason it matters. The pattern the instruments are reading at Campi Flegrei right now has historical precedent. That precedent is the last eruption. And that eruption came after the same kind of slow, sustained, accelerating uplift, eventually focused, eventually critical, that the instruments are currently recording. The 1538 eruption was not a supervolcanic event. It was, on a geological scale, modest. A new hill on the landscape, 24 people killed, the local harbor altered. The caldera has a different scale of event in its history, 2 of them. 39,280 years ago, give or take a century, Campi Flegrei did something that had no witnesses and left its fingerprint across a continent. The Campanian ignimbrite eruption, the largest volcanic eruption in Europe in the last 200,000 years. Rated a volcanic explosivity index 7, 1 step below the theoretical maximum of 8 in the range occupied by supervolcanic events. Between 179 and 243 cubic kilometers of magma ejected. Pyroclastic flows, rivers of superheated gas and rock traveling at hundreds of kilometers per hour, covered 30,000 square kilometers. An area the size of Belgium, scoured by flows moving too fast to outrun, the eruption column punched into the stratosphere. The ash layer, the Campanian ignimbrite, the Y5 tephra, blanketed more than 3 million square kilometers, from southern Italy east to the Russian plains, more than 2,200 kilometers away, southward to the North African coast. It has been found in ice cores from Greenland. It is a global stratigraphic marker, a timestamp in the rock record of an entire hemisphere. Climate models suggest the eruption cooled Europe by 3.6 to 7.2 degrees Fahrenheit in the year that followed, depending on how much sulfur was released. For context, that cooling range overlaps with or exceeds the temperature drop of the Little Ice Age, a multi-century cold period from the 14th to the 19th century that produced widespread famine and social upheaval across Europe. The timing coincided with the demise of the Neanderthals in Europe. The coincidence has been debated by anthropologists for decades. Correlation is not causation, and the extinction of a species is never a single event story. But the eruption, coinciding with the already precarious position of a population under pressure from anatomically modern humans and the onset of Heinrich Event 4, one of the coldest, driest phases of the late Pleistocene, is at minimum a plausible contributor. The rock those pyroclastic flows left behind is the tufa, the pale yellow stone, that Naples' historic buildings are built from. Walk through the old city, and you are walking through the compressed ejecta of the eruption that may have ended Neanderthal Europe. The Campanian ignimbrite is literally the city's foundation. Then, roughly 15,000 years ago, a second caldera-forming eruption, the Neapolitan yellow tuff, VI6, approximately 40 cubic kilometers ejected. Smaller than the Campanian ignimbrite, but still a civilization-scale event. That eruption created the inner caldera structure visible today. Then, approximately 3,000 years of relative quiet. Then, about 4,800 to 3,800 years ago, a period of significant eruptions within the caldera. Then another extended quiet. And then, after about 3,000 years of quiescence, the sequence that ended in 1538. I'm not telling you this to suggest that a Campanian ignimbrite scale event is imminent. It is not. The current evidence points towards something far more modest than a VI7. What I'm telling you is what this caldera is. The 1538 eruption produced a hill. The 39,000-year eruption produced an extinction-level climate event. The system has produced both, and everything in between. The planning documents and evacuation frameworks are calibrated to the modest end of that spectrum, as they should be, because that is the most probable scenario. But the calibration is worth understanding, because planning for the probable is the right approach, and simultaneously acknowledging what this system is capable of, at its maximum, is the honest one. And this is where the story takes a turn that most coverage of this week's swarm is completely missing. The earthquake happened, the schools closed, the buildings were inspected. The news cycle moved on, and buried in that transition, an important question didn't get asked. What is the state of the buildings that were inspected? Not just today, but cumulatively. After 2 decades of continuous seismic activity, after every swarm since 2022, which the AI catalog shows generated not 12,000 earthquakes, but more than 54,000. After the 4.6 in June 2025, the 4.4 in March 2025, the 3.9 in February 2025, and now the 4.4 of May 21st, 2026. There's a thread here that runs directly from the seismic record to the evacuation plan, and it's the one I want to pull. The Italian government allocated 52 million euros for structural inspections and civil protection measures in 2023, following a string of magnitude 4+ earthquakes. That was real. That was significant. Inspectors went out, buildings were assessed, some were declared uninhabitable. Residents in parts of Pozzuoli's historic center were displaced. But here's what I keep coming back to. In 1982 to 84, the crisis that prompted the evacuation of 40,000 people and the permanent relocation of those residents to Monteruscello, the total event count was approximately 16,000 earthquakes over 2 years. That crisis ended. The damage was assessed. People were moved. The current episode has generated, per the Stanford AI catalog, which is the most complete count available, more than 54,000 earthquakes between January 2022 and March 2025 alone. And the current episode has been running at lower intensity but continuously since 2005. 21 years of seismic stress on structures that were not young in 2005. The 1984 crisis was described by researchers at the time as producing social impact and economic loss comparable to an actual eruption. The quote came from the Global Volcanism Program's June 1984 bulletin. The length of the present crisis, 2 years since the beginning of uplift, has produced a social impact and economic loss comparable to that of an actual eruption. The researchers suffer from the accumulated stress of being responsible for the lives of thousands of people. That quote described a 2-year crisis. The current unrest episode has lasted 21 years. The evacuation plan for the Campi Flegrei red zone covers approximately 500,000 people across the municipalities of Pozzuoli, Boccoli, Monte di Procida, and Quarto, and portions of Naples, including the Bagnoli and Fuorigrada districts. The yellow zone, the area subject to significant ash fallout in an eruption scenario, encompasses an additional approximately 800,000 people. Under a red alert, the mandatory evacuation window is 72 hours. The plan is real. It has been updated. The Naples City Council voted unanimously to approve the latest version in September 2024. But the plan was designed for a specific scenario, a volcanic event, arriving with volcanic-scale warning signals from a city and building stock that is nominally intact. It was not designed for a scenario where the building stock has been subjected to 2 decades of continuous low to moderate seismic loading before the main event begins. It was not designed for a scenario where a population that has been living with chronic displacement and property damage for years may resist a mandatory evacuation order, even a legally enforced one, because they have been asked to leave before and came back to find their homes still standing.
This is not a criticism of the plan. It is an acknowledgement of what the plan was designed for and what the ground conditions now are. Those are not the same thing. In Chunk 3, we go into the full implications, what the 3 possible outcomes of the critical transition actually look like, what the compound vulnerability with the Vesuvius red zone means for logistics, and the specific signals that would tell scientists the dynamic is changing. We also address the fringe claims directly, because they are circulating and because the real story doesn't need embellishment.
20 kilometers to the east of Campi Flegrei, visible from the hills of Pozzuoli on a clear day, sits Mount Vesuvius. You know Vesuvius. Pompeii, 79 of the Common Era. It is probably the most famous volcano in the world, and its reputation is entirely earned. The eruption that buried Pompeii and Herculaneum was a VEI-5 event, a Plinian column that collapsed to produce the pyroclastic surges that killed most of the victims. Vesuvius has erupted more than 30 times since '79. Its last eruption was in 1944. It sits, fully awake and monitored, inside the metropolitan area of one of the most densely populated cities in southern Europe. Campi Flegrei and Vesuvius are separate volcanic systems. They have independent magmatic sources. An eruption at one does not cause an eruption at the other. This is not a story about simultaneous eruptions. But here is the thing that the separate system framing obscures. They share a city. And more specifically, they share the infrastructure through which a city evacuates. The Vesuvius Red Zone covers 25 municipalities in the provinces of Naples and Salerno. The red zone population in that zone is assessed by the Italian Civil Protection at approximately 700,000 people across its two risk tiers. The Campi Flegrei red zone population is approximately 500,000. Combined, the two red zones encompass well over 1 million people, and they both evacuate through Naples. The official Italian Civil Protection Emergency Plan for Campi Flegrei lists the primary evacuation infrastructure explicitly: Naples Central Station at Piazza Garibaldi, the Naples Port Seaport Station, the Afragola high-speed rail terminus. These are the three major nodes through which the 500,000-person Campi Flegrei red zone would be moved. The residents of Pozzuoli would go to Lombardia, Boccoli to Umbria and Marche, Monte di Procida to Abruzzo and Molise. 3 days to move 500,000 people through 3 transit hubs, on trains, buses, and ships. The Vesuvius evacuation plan uses the same infrastructure, the same stations, the same port. Different twinned regions, but the same choke points. This is not a logistical argument for pessimism. It is a structural observation. The two systems are independent in their geology and independent in their alert levels. Campi Flegrei is at yellow. Vesuvius is at green. There is no current scenario that has both systems escalating simultaneously, but the planning frameworks for each were designed with one system in mind at a time. The overlap, the shared rail lines, the shared port, the shared motorway corridors, means that even a moderate escalation at Campi Flegrei, short of a full red alert, begins degrading the capacity that would be needed to respond to an elevated signal at Vesuvius at the same time. 2 patients, 1 operating theater. And there's a third element to the compound vulnerability that doesn't get mentioned in the planning documents because it's sociological rather than geological. The population inside the Campi Flegrei red zone has been living with this crisis for 2 decades. They have been shaken by thousands of earthquakes. They have watched their buildings crack. They have lived through displacement, property loss, the closure of the historic Solfatara tourist site after a fatal accident in 2017, and years of uncertainty about what comes next. Research on disaster psychology consistently finds that populations with chronic exposure to low-level threat develop what psychologists call habituation, a reduction in the urgency of the response to each new event. Not indifference, but a recalibration of what counts as an emergency. The evacuation plan assumes 3 days and voluntary compliance during a pre-alarm phase, followed by mandatory evacuation under red alert. It does not fully account for a population that may be 3 evacuations deep into its tolerance for disruption by the time the red alert arrives. The May 21st school closures for building inspections are the latest in a series of such disruptions stretching back years. Each one prompts people to assess, is this it? Each time it is not, the threshold for the next mobilization rises slightly. This is not a failure of the plan. It is a reality the plan exists within. Most coverage of Campi Flegrei mentions the 1982 to 84 crisis the way you'd mention a cautionary tale. The last time things got serious, 40,000 people were evacuated, and then everything settled down. That framing is technically accurate and deeply misleading. Let me tell you what the crisis actually looked like from the inside. By the summer of 1982, the ground at Pozzuoli had been rising slowly since the late 1960s. The uplift from the 1969 to 1972 episode had been roughly 170 centimeters at its maximum. Then the ground had subsided. Then, starting in the summer of 1982, it began rising again, faster. By December 1983, the ground had risen 110 centimeters since January of that year alone. The harbor at Pozzuoli was becoming unusable. Ships that had docked there for generations could no longer approach without running aground on a seafloor that kept climbing to meet them. The harbor required constant dredging. Buildings in the historic center of Pozzuoli, structures that had stood for centuries, some built from the same companion tufa that the 39,000-year eruption deposited, began cracking. Streets buckled. Water and gas infrastructure split and failed. The seismicity escalated. More than 16,000 earthquakes in 2 years. Some were strong enough to crack buildings that had survived the uplift intact. The earthquakes were shallow, as they are now, as they always are at Campi Flegrei during Bradysism, which means the shaking was felt acutely at the surface. Not deep, attenuated rumbling, but sharp, close physical violence to structures that were already stressed. In November 1982, moderate seismic activity prompted the first precautionary closures. The crisis became impossible to manage at arm's length. By early 1984, a magnitude 4 earthquake and the cumulative damage from thousands of smaller events forced a decision. 40,000 people in the central historic district of Pozzuoli would be relocated. They were moved to Monteruscello, a new town built on higher ground, outside the caldera's most vulnerable zone. The Italian government funded the construction. The relocation was permanent. The people who moved to Monteruscello did not return. 40 years later, parts of Pozzuoli's historic center that were evacuated in 1984 have still not been fully repopulated. The streets exist, some of the buildings were repaired, but the community that lived there didn't come back whole. Tiziana Vanorio, now a Stanford researcher who studies the rock physics of volcanic systems, grew up in Pozzuoli and was forced to evacuate in the 1980s. Speaking to journalists in 2025 about the current unrest, she said, "It's been a challenge for the last 3 years. Many buildings have been damaged by the continuous shaking, and some people don't have homes." The 1984 Smithsonian Global Volcanism Program Bulletin, written in real time by the researchers monitoring the crisis, includes a passage I want to read carefully. "The high density of population of the area, 250,000 people live within the caldera, is posing a tremendous problem with respect to the measures that should be taken to reduce the hazard. The length of the present crisis has produced a social impact and economic loss comparable to that of an actual eruption." The researchers devoted to the difficult task of monitoring and understanding the development of the phenomenon suffer from the accumulated stress of being responsible for the lives of thousands of people. That was written about a 2-year crisis. The current episode, depending on how you date its start, has run for 21 years. And the UCL analysis tells us that the 1984 crisis left the crust weaker than before it started. The current episode has built on that weakened foundation. Every swarm since 2005 has added its contribution to the damage ledger. The cumulative account is now at 140 centimeters of uplift and more than 54,000 earthquakes in just the last 3 years of enhanced detection. The 1984 crisis was the most severe in modern recorded history, and it ended without eruption, and it permanently displaced 40,000 people and produced economic damage on the scale of an eruption. That is the lower bound, not the upper, of what the current episode might eventually produce. I want to pause here and deal with something that comes up in the comments and the forums whenever Campi Flegrei gets attention. There are 2 specific claims circulating. The first is that Italian or European authorities are suppressing or minimizing the real danger, that the data is being managed to avoid panic. The second is that industrial activity, specifically geothermal energy extraction, is causing or significantly amplifying the unrest. Both claims deserve a direct answer. On the suppression claim, the data at Campi Flegrei is, by any objective measure, among the most publicly accessible for any volcanic system on Earth. The Vesuvian Observatory publishes a weekly bulletin containing earthquake counts, maximum magnitudes, ground deformation rates, and fumarole temperatures. It is publicly available on the website. The Italian Civil Protection publishes its full national emergency plan, including the red zone boundaries, the twinned regions, the evacuation logistics, on protezionacivile.gov.ie. The Stanford AI study that expanded the earthquake catalog from 12,000 to 54,000 was published in Science, one of the most prominent peer-reviewed journals in the world, with open methods. The April 2026 Zaccagnino finite time singularity paper was posted to the public preprint server arXiv before peer review, not after. The INGS itself issued a press release about the Calero sulfur isotope paper, describing the finding as an important anomaly linked to the contribution of magmatic gases. If there is a suppression operation underway, it is the least effective suppression operation in the history of volcanology. The actual complaint, I think, is different. What critics are registering is a frustration with measured, qualified scientific language, the careful hedging, the emphasis on uncertainty, the eruption is not imminent, reassurances, when the data, as they read it, is alarming. That frustration is understandable. The honest answer to it is, the scientists monitoring Campi Flegrei are not suppressing alarm. They are doing their jobs, which require them to state what the data shows and not what it doesn't show. When Kilburn says, eruption is not inevitable, that is not a reassurance designed to prevent panic. It is the accurate statement of the current evidentiary state. And when the Zaccagnino paper says the system is approaching a critical mechanical threshold, that is not a suppressed bombshell, it's what it says, in the abstract, available to anyone who searches the paper's arXiv identification number. On the geothermal claim, I want to be precise, because there is a version of this that has genuine scientific substrate, and a version that doesn't. the version that doesn't, the claim that industrial geothermal extraction is driving or causing the multi-decade bradyseismic escalation at Campi Flegrei. The bradyseismic episodes at this caldera predate modern industrial activity. The first systematic documentation is from the Serapeum columns, 2,000 years of ground movement recorded in stone, most of it before industrial civilization existed. The 1950 to 52 and 1969 to 72 episodes both preceded any significant geothermal development in the area. The spatial footprint of the current unrest, caldera-wide with hypocenters extending to 3.7 kilometers, is inconsistent with the shallow, localized signature of induced seismicity from fluid injection or extraction, which typically manifests within a kilometer or two of the injection point. The mechanism is wrong, the scale is wrong, the timing is wrong. The version that does have scientific substrate, a 2026 paper in Geoscience Frontiers found evidence that heavy rainfall can modulate bradyseismic activity at Campi Flegrei. This is a real peer-reviewed finding. It shows the hydrothermal system is sensitive to surface inputs, that changes in groundwater pressure from rainfall can influence the rate and pattern of the earthquakes and uplift. This is structurally similar to the induced seismicity argument, which is presumably why the claim persists. But modulating an ongoing process is not causing it. The rainfall finding is consistent with a hydrothermal system that is already highly pressurized responding to additional inputs. The driver is the magmatic volatile flux from below. The rainfall is at most a modifier of timing and intensity at the margins. The real human fingerprint on Campi Flegrei's risk is not geothermal extraction. It is the decision, made over decades by successive governments and planning authorities, to allow population density inside the caldera to continue growing, and to delay investment in building resilience and early public education, after the 1982 to 84 crisis demonstrated exactly what a moderate unrest episode costs. The investigation is now deep enough that I want to be specific about what we know, what we don't know, and what specific signals would change the picture. Because monitoring a supervolcano is a phrase that can mean anything. I want to tell you what it actually means, what the scientists are looking for, what data would move the needle, and what would constitute a genuine escalation of the alert level. The current picture has these confirmed elements. Continuous ground uplift at 10 millimeters per month, sustained since 2025 at a minimum. Cumulative uplift since 2005 of approximately 140 centimeters. Seismicity increasing in frequency and maximum magnitude since 2022, with 5 earthquakes above magnitude 4 in 2025 alone, and the highest recorded at 4.6. A ring fault now sharply resolved, being progressively activated, with all seismicity strictly above 3.7 kilometers depth. CO2 flux at Pisciarelli above 600 tons per day, erupting volcano scale. Isotopically light sulfur appearing in fumarole emissions since 2018, attributed to decompression-driven degassing of mafic magma at 6 or more kilometers depth. The crust at approximately one-third its 1984 tensile strength, a finite time singularity model projecting a critical transition by approximately 2030 to 2034. The current alert level, yellow. What would change the picture toward escalation? The first signal to watch is seismic activity below 3.7 kilometers. The Stanford science paper was explicit. To date, no direct signature of upward migration of magma has been observed, and no seismic activity below 3.7 kilometers on or inside the ring fault system has been detected. That depth boundary is currently the most important single threshold in the monitoring picture. If earthquakes begin appearing below that depth, along the ring fault, it would mean the brittle ductile transition is being crossed, that the fracturing is reaching into rock that was previously too hot and ductile to break. That would be a significant change in the physical state of the system. The second signal is the SO2 to CO2 ratio at Pisciarelli. Right now the system is speaking CO2, the deep, early signal. And it is speaking isotopically light sulfur in the form of H2S, which appears at depth before SO2 is formed. When SO2 begins appearing in significant quantities in the fumarole emissions, it means the magma is much closer to the surface, within roughly a kilometer or two. That transition in the gas ratio is one of the clearest pre-eruptive signals available at shallow calderas. INGV's 4 geochemical monitoring stations are watching for it continuously. The third signal is an acceleration in the ground uplift rate. 10 millimeters per month has been the sustained rate. If that rate doubles to 20 millimeters per month and sustains, it would indicate that the pressurization driving the uplift has intensified significantly. The pre-1538 sequence showed exactly this, a shift from slow, sustained caldera-wide uplift to a focused, accelerating deformation in the vent area over the final 2 years. And the fourth signal, one that doesn't require a seismograph or a gas analyzer, is physical rupturing of the surface. New fissures opening. New fumarolic vents appearing outside the existing Solfatara and Pisciarelli fields. Anomalous heating of the soil. These would indicate that the pressurized hydrothermal fluid has found new pathways to the surface, which would itself mean the crust above the reservoir has been broken in new locations. None of these signals are present today beyond what has already been described. The uplift rate is 10 millimeters per month, not 20. The fumaroles are running CO2 and isotopically light H2S, not SO2. The seismicity is above 3.7 kilometers, not below. The surface shows the established Solfatara and Pisciarelli activity, not new ruptures.
But the system is at approximately one-third its 1984 tensile strength, is projecting a critical threshold in the early 2030s, and just generated a magnitude 4.4 swarm on its newly revealed ring fault 2 days ago. That is the honest position. Confirmed facts on one side, active thresholds being approached on the other. And in Chunk 4, we hold both of those things together and work through what they actually mean.
There are 3 honest positions on the current data at Campi Flegrei. I'm going to give each one its full weight. Not a straw man, not a token alternative, but the strongest version of each reading the evidence actually supports. Because this is a system where the uncertainty is real, and the uncertainty deserves respect. Start with the most reassuring interpretation. Not because I think it's the most likely, but because it is grounded in evidence. It has credentialed advocates, and it would be dishonest to present it otherwise. The caldera has been through 4 modern unrest episodes. 3 of them, 1950 to 52, 1969 to 72, and 1982 to 84, ended without eruption. The ground came down. Twice it came down rapidly. The dramatic 6-foot uplift of the 1982 to 84 crisis was followed by significant subsidence, the ground falling about 3 feet in the years after the crisis peaked. The system relaxed. The pressure was released in a form that didn't rupture the surface. Stefano Carlino, a researcher at the Vesuvian Observatory and co-author of the UCL tensile strength study, was explicit in his assessment when the 2023 paper was published. Campi Flegrei may settle into a new routine of gently rising and subsiding, as seen at similar volcanoes around the world, or simply return to rest. We can't yet say for sure what will happen. The most critical piece of evidence in the reassuring reading is the depth constraint from the Stanford AI paper. No seismic activity below 3.7 kilometers on or inside the ring fault system. That means the fracturing, the progressive destruction of the crust that Kilburn's model tracks, is confined to the shallow hydrothermal zone. The deep rock between 3.7 kilometers and the magmatic source is not being broken. There is no seismic signature of magma forcing its way upward through that interval. The volatiles being released at depth are migrating upward through the hydrothermal system, a pathway that has been open for decades, rather than breaking new rock to create a fresh conduit. The Zaccagnino paper itself is careful. No evidence of imminent eruption was found. The critical transition between 2030 and 2034 is a mathematical projection of current trends. It assumes those trends continue unchanged. If the system undergoes a partial pressure release, a large but non-eruptive seismic event, or a significant phreatic explosion, or a rapid escalation of fumarolic output that bleeds pressure from the system, the singularity model's projection changes. The paper explicitly states the outcome of the critical transition remains uncertain, and there is historical precedent for long sustained unrest periods at caldera systems that ended without eruption. Yellowstone, Rabaul, Long Valley all have extended histories of seismicity and ground deformation that did not culminate in eruption. Caldera unrest is, statistically, far more commonly non-eruptive than eruptive. The most probable outcome of a given unrest episode at most calderas is that the system eventually settles. This interpretation is not wrong. It is fair. It accounts for the actual data. The intermediate interpretation is where the weight of the peer-reviewed literature actually sits. Not the most alarming reading, not the most reassuring, the center of the distribution. The current unrest episode is not a repeat of previous cycles. The UCL analysis shows cumulative, irreversible damage to the crust's tensile strength, 2.5 to 3 times weaker than 1984. Each previous episode added to the ledger of permanent structural change. This episode has been running 21 years, longer and more sustained than any of the previous 3. And unlike the previous 3, it has not yet subsided. It is still going. The Zaccagnino paper's finding that the acceleration fits a finite time singularity rather than exponential growth is not a matter of model preference. It represents a different underlying physical process. Exponential growth can continue indefinitely, even if it speeds up. A finite time singularity cannot. The The mathematics of a finite time singularity require a regime change at T sub c. The question is not whether a transition occurs, but what form it takes. And importantly, the regime change does not have to be volcanic, but it has to be something. The current state, progressive crust weakening, sustained hydrothermal pressurization, 10 millimeters per month of uplift, cannot continue without limit. The isotopically light sulfur finding from the Caldera 2025 paper is not explained by the hydrothermal system alone. The team's modeling, published in Nature Geoscience and supported by Woods Hole in Cambridge, attributes the signal to mafic magma at 6 or more kilometers depth. This is not a shallow hydrothermal signature, it is a deep magmatic one. And it has been building since 2018, 7 years of an unprecedented geochemical shift, in the same multi-decadal record where the previous most alarming signal appeared during the crisis that prompted the evacuation of 40,000 people. The current change is described as more pronounced than what was seen then. The NIES 2025 paper's comparison of the current unrest to the pre-1538 sequence is not presented as a forecast, but the structural similarity is its own data point. The maximum earthquakes are similar. The uplift rates are similar. The pre-1538 sequence ran for approximately 100 years before culminating in eruption. The current cycle, counting from the first 1950 episode, is 76 years old. The intermediate reading holds these findings together, honestly. Something in the early to mid-2030s is likely to represent a critical transition in the system's state. The transition may not be eruptive. The probability distribution includes many non-eruptive outcomes. But the transition is projected. It is grounded in convergent evidence from multiple independent measurement streams, and it is not the kind of thing that can be managed by treating each week's seismic bulletin as a standalone event. The intermediate reading is, this system is approaching something. The monitoring signals will tell us, with more lead time than the pre-1538 sequence had access to, what form that something is taking. The question for 500,000 people and their government is whether the monitoring, the communication, and the evacuation infrastructure can translate that lead time into action. The most concerning interpretation is not a prediction. I want to be very clear about that. It is a physically possible worst case, grounded in the system's known capabilities. The deep mafic magma signal at 6 or more kilometers, the source of the isotopically light sulfur, is, in the Caldera team's modeling, consistent with a magma body that is actively degassing under decompression. Decompression-driven degassing means the pressure on the magma is decreasing. The load above it is being reduced. The most natural explanation for that is the sustained ground uplift itself, which decompresses the rock as it expands. The deep magmatic system and the surface uplift may be in a feedback loop. The uplift decompresses the magma, which releases more volatiles, which pressurizes the hydrothermal system, which drives more uplift. If that feedback loop is correct, then the convergence to a critical transition is not just a mathematical projection of a trend. It is the physical description of a system driving itself toward a threshold. The accumulating damage to the crust, now at 1/3 its 1984 tensile strength per Kilburn's analysis, means each new pressure pulse meets weaker and weaker material. And the Zaccagnino model says the pressure pulses are themselves accelerating. The pre-1538 sequence adds context. That sequence showed caldera-wide uplift for roughly a century, then a sudden focusing of deformation into the area that became the vent. The 2-day warning before the actual eruption was essentially the only direct precursory signal that people at the time could read. In 1538, the instruments were the crack in the ground and the sea pulling back from the shore. In 2026, the instruments are 54,000 seismically detected earthquakes and 4 continuously operating geochemical stations. The monitoring is incomparably better. But the question of whether a 72-hour mandatory evacuation window is sufficient to move 500,000 people through 3 transit hubs is independent of how good the monitoring is. In a worst-case scenario, not the probable scenario, but the physically possible one, the critical transition, projected for 2030 to 2034, involves not a Bradia seismic peak and subsequent subsidence, but a rupture of the ring fault. A caldera-forming eruption at Campi Flegrei would not be the first in human history. The Campanian ignimbrite was one. The scenario that the Italian Civil Protection's red zone planning is calibrated against is not caldera-forming. It is a VI 4-5 event, a subplinian eruption from one of the caldera's existing vent structures. That is already, by any measure, an extraordinary event. A VI 4-5 eruption at Campi Flegrei would generate pyroclastic flows capable of reaching the western outskirts of Naples within minutes, ash fallout across the region. a multi-day event requiring the full execution of an evacuation plan for 500,000 people in the red zone and up to 800,000 more in the yellow zone. That is not the supervolcanic scenario. That is not Companion Ignimbrite. That is the middle of the distribution of possible outcomes from a critical transition at this system. And it is what the planning documents are actually prepared for. The question is whether the preparation is sufficient and whether the lead time the monitoring provides will translate into a response that matches the scenario. I hold this interpretation as a physically grounded possibility, not as a prediction. The data does not tell us which of the three interpretations is correct. What the data tells us is what each one costs if it turns out to be the right one. Let me lay this out as plainly as I can. Confirmed. The ground beneath Campi Flegrei has been rising continuously for 21 years at 10 millimeters per month as of early 2026 for a cumulative total of approximately 140 centimeters. The seismicity has increased in frequency and maximum magnitude since 2022. 5 earthquakes above magnitude 4 occurred in 2025. A magnitude 4.4 struck 2 days ago. The AI expanded seismic catalog revealed a sharply defined ring fault system with all seismicity above 3.7 kilometers. CO2 flux at Pisciarelli exceeds 600 tons per day. Isotopically light sulfur has been appearing in fumarole emissions since 2018, attributed to magma at 6 or more kilometers depth. The crust's tensile strength is approximately 1/3 its 1984 value. A finite time singularity model projects a critical transition between 2030 and 2034. The current alert level is yellow, uncertain, whether the critical transition will be eruptive or non-eruptive. Whether the deep mafic magma signal represents an intrusion actively approaching the shallow system or a stable deep source releasing volatiles through existing pathways. Whether the damage to the building stock inside the red zone, accumulated over 2 decades of seismic loading, is compatible with a rapid execution of the 72-hour evacuation plan. Whether the SO2 to CO2 ratio at Pisciarelli will begin shifting toward higher SO2 before the projected critical transition window or not until during it, unknown. The specific triggering mechanism if a transition occurs and whether it will be preceded by minutes, hours, or days of clear precursory escalation. Whether the 54,000 earthquake catalog represents the full picture of what the ring fault system has been doing, or whether even more activity exists below the current AI detection threshold. What the pre-eruption sequence will look like, if there is one, given that the 1538 2-day warning is the only direct historical analog, and that analog came after a century of lower-grade unrest, not a 21-year sustained uplift episode. The specific data that would change the picture. Seismicity below 3.7 kilometers on the ring fault. A significant increase in the SO2 fraction of fumarole emissions at Solfatara or Pisciarelli. An acceleration in the ground uplift rate beyond 10 millimeters per month. New surface ruptures or fumarolic vents outside the established degassing areas. These are the signals INGI's monitoring network is designed to catch. What I want you to hold at the end of this investigation is not alarm and not reassurance. Both of those are simpler than the evidence warrants. What the evidence warrants is this: a system that has been methodically changing its own physical state for over 2 decades in every measurement channel simultaneously in ways that converge on a projected critical threshold within a decade is a system that deserves sustained, informed attention. Not panic. Attention. The researchers who study it are giving it that attention. So are we. The name Campi Flegrei comes from the Latin, burning fields. The Greek writer Strabo, writing roughly 2,000 years ago, described the Pozzuoli area as a plain shut-in all around by exceedingly hot ridges, full of fumaroles like chimneys, with a rather noisome smell. He wasn't filing a disaster report. He was describing the neighborhood. The burning was normal. It has always been normal. People built their homes here, raised their families here, buried their dead here, because the burning fields were also fertile fields, warmed by the earth, facing a blue bay, surrounded by the produce that grew where nothing should have grown. The volcano was not separate from the life, it was the condition of the life. The Serapeum columns are still standing, borings at mid-height. Marine mollusks who haven't been there in centuries left their record. The columns have recorded 11 meters of sinking and 12 meters of rising, a total journey of more than 23 meters, up and down, in the time since 2 Roman workers cut them from stone. They are the world's longest-running ground movement log, and they are still logging. Since 2005, the ground at Pozzuoli has risen approximately 140 centimeters. At the current rate of 10 millimeters per month, by 2034, the outer edge of the Zaccagnino critical transition window, the system will have added roughly another 96 centimeters to that total. The cumulative uplift since 1950 at that point would approach the full 4 meters that the columns recorded as the total rise, culminating in the 1538 eruption. I'm not telling you that's the trajectory. The data doesn't tell me that with certainty. What the data tells me is that the trajectory is the right question to keep asking. The scientists at the Vesuvian Observatory, the people who publish the weekly bulletins, who maintain the monitoring network that has been running continuously since 1972, who wrote the papers I've been citing, are watching. Xing Tan and Gregory Barroza at Stanford have the AI system running. Stefano Caliro and his team are reading the chemistry at the Solfatara every month. Christopher Kilburn is tracking the tensile strength. Davide Zaccagnino is updating the singularity model as new data arrives. Sebastian Heinzel is refining the earthquake interaction model. The monitoring is, by the standards of volcanic surveillance anywhere on Earth, exceptional. The warning systems are real. The evacuation plans exist and have been tested. What remains is the gap between what the physics is projecting and what the infrastructure can execute. That gap is not ignorance. It is the honest recognition that a system approaching a critical mechanical threshold in the early 2030s, beneath 500,000 people and their city, is a problem of a scale and a character that good science can describe and good planning can address, but cannot fully resolve in advance.
The burning fields have been burning since before Rome. They will burn after us. The question they're asking right now, the question the data is posing, is whether the current burn is heading towards something different from what came before. We will keep watching. The INGV bulletins publish every week. When the chemistry shifts, when the depth boundary moves, when the ring fault speaks in a new way, we'll be here. The columns are still recording.